As we continue our study of sample spaces, remember that sample spaces are really just mathematics sets. And we're going to look at some examples. But before we get there, remember that a mathematics set can be discrete or continuous, and it can be finite or infinite. And the same applies to sample spaces. Sample spaces can be discrete or continuous, and they can be finite or infinite. And this applies to how we develop a probabilistic system, how we design our experiment in a probability system in terms of whether it is discrete or continuous, and whether it's finite or infinite. Now, the simplest form of probabilistic system that we can look at is that of a discrete finite sample space. And an example of that would be two successive flips of a coin. So we can look at that in one of two ways. The first representation would be more of a XY chart, if you will. And so in that case, we really get this first flip and second flip mentality where we can say, hey, on the first flip, we were tails. So we know that we're going to be in this column here. And on the second flip, we got heads. So we're going to be in this cell. Tails, then heads. Or maybe it's a little bit different and we say on the first flip we got heads, and on the second flip we also got heads, so now we're going to be in the heads cell. And so this is a way to ultimately identify what a probabilistic system's possible outcomes are. So if you look at that, you have a tails, then tails, a heads, then tails, and so on, that can be assigned to each of these cells. And you can also go back and assign a probability. So let's say that this one is 0.25, and so is this one. It's a fair coin. Now, the other way to look at these systems is as more of a staged or phased operation, as opposed to looking at it like an XY system. So the same two flips of a coin, we can look at it as different phases. So maybe the first phase is that we rolled a heads. And then after that, we can roll either a heads or a tails. And then on the other side, maybe our first flip was a tails. And then coming off of that, we can have either heads or tails again. And so now at the end of this phased system, we have really phase 1 and phase 2. And we can ultimately dictate now what the probability at each of these possible outcomes are. So this is the heads probability. This is the heads tails probability. This is a tails heads, and then a tails tails. Again, just a different way to look at the same type of system, and the same ultimately sample space. My sample space is each of these possible outcomes over here on the right. Now, this type of diagram we call a tree. Why? Because it has branches. So each of these nodes here is a branch. It's a different decision-making point where there's a different probability for each of those branches. Now, the endpoints over here we call a leaf, or in the plural, we call them leaves. And those leaves are ultimately the end points of those probabilistic systems. Now, in both cases, whether we look at the tree or at our little XY chart, there are a total of 4 possible outcomes for 2 flips of a coin. Now, because of this, there are a limited number or finite number of outcomes, and they are each uniquely identified as a very specific number. And so in that case, they are discrete. Now, if we look at a slightly different system, let's look at an example of a continuous finite sample space. And so this may be you're throwing a dart at a dartboard. And for simplicity, this dartboard is going to be a square, and it has an X and a Y coordinate system. So in this case, the probability of throwing a dart at a specific point on this dartboard is going to have a probability associated with it. And my sample space, let's say, is from 0, 0 to 1, 0 and 0, 1. So it can go up to 1 in both axes. And I end up having a dart that lands right here. Well, what is that location? If we assume that that's measured to infinite precision, then that becomes a continuous finite sample space where this value, say, is going to be 0.8888 repeating, intersected with 0.899 repeating, or whatever location that actually is on the dartboard. So in this case, we have a continuous system where the range of individual possibilities in the system is actually infinite. It can land anywhere in this dartboard, and there are infinitely many distinct points within this finite space that goes from 0 to 1 in 2 axes. Now, that has a critical assumption, which is that whenever you throw the dart, it does land within that area, but we'll assume that we actually know how to play darts. So in this case of an experiment, the sample space is really just the set of XY pairs. And again, there are an infinite number of XY pairs, so therefore this is a continuous system. But the XY pairs are limited in their range, so it's still finite.